Okay, good afternoon, everyone. Welcome to the graveyard shift. My name is Keith Braithwaite. I work for Sulgate Engineering in London. It's a Swiss company, but I work in the office in London, and I lead a group of consultants and engineers called the Centre for Agile Practice. Our day job, our bread and butter, is building software for paying customers, which we do using Agile methods. And we also train and coach in those techniques as well. But everything that we do in our training and consultancy is based on our practical experience of building software for paying customers, and the things that I'm going to talk to you about today are also based on our practical experience of doing that. There's nothing theoretical about it. This is all things that we have seen work. And the topic is requirements. Some of you may have seen this cartoon before, and it illustrates some of the problems with getting software built. And the punchline really is the tire on the rope in the bottom right-hand corner. If we could get to understand the thing that our clients and our customers really want to do, and build something which addresses that need directly, they and we would end up in a happier situation. So we want to try and find techniques to avoid the problem illustrated here with the disparity between the nice blue comfy chair and what actually gets installed, by finding a way to understand what customers really want. And this is not a new idea. It's well established in the industry and in the literature that one of the most common reasons why software development projects are unsuccessful is not because the development team did a poor job of building the software. That does happen, but it's not the most common problem. The most common problem is that they do a good job of building the wrong thing, or of building something which turns out to be the wrong thing by the time it is delivered, or that it may have seemed plausible at the beginning of the project. And one response to that, which has been taken in the industry in past, is to sink a lot of effort into producing big, detailed requirements documents with some sort of gateway or review or checkpoint at the end of an analysis phase to try and get that right. Anyone from here familiar with projects that work that way? A few of you, yeah. In the Agile world, we don't want to do that, because that's one of the reasons why we end up building something which turns out to be the wrong thing. The length of time it takes to produce those documents means that the world changes while we are not paying attention. It's also very slow, it's very expensive, and we cannot respond to change as quickly as we would like if we work that way. So in the Agile world, we don't want to do that. The other thread that's quite common in the industry is that people who are educated as programmers are educated to think about what they do and to think about the world in very mathematical terms. And so there is a tendency to think that if only we could get the requirements documents to be precise enough, then we would be okay. And that the problem maybe is that we let our customers get away with making vague statements about requirements. And so we try to bring them to us as technologists and make them express their ideas about what they want in very technical language. The problem is, as I've shown in that second or that bottom proposition, there do not exist any customers who understand how to do this. So that's a problem. That's a big part of why the formal methods world has not been tremendously successful. Because it turns out people, and customers are people, difficult as that may be to believe at times, people do not understand the world in terms of rules. There is an idea which goes all the way back to Aristotle, and perhaps earlier, that we understand the world in terms of categories or concepts, which are almost the same thing, and that you can tell if an object belongs to a category because with the category comes a definition. And definitions in that model are constructed from individually necessary and jointly sufficient definitions or predicates. Definition is constructed from predicates. And if all and only the predicates that belong to the category are true of the object, then the object is a member of the category, and that's how we understand the world. This is a very attractive idea to mathematicians. It's a very attractive idea to people who might want to, say, build a relational database, because the predicates that form the definition of the category can very easily be turned into the columns of a table that records entities that correspond to the objects in the category, and so on and so on and so on. It's very attractive to people who want to write code. Unfortunately, that's not the way people think about the world. And this is empirically demonstrated. Since the mid-1970s, psychologists have done experiments to find out how people understand the world. And it is not in terms of categories with definitions built out of predicates. That's just not what people do. What people do is they remember instances, and they recognize the similarities between those instances. And when a new thing that they haven't seen before comes along, they think about how similar it is and how different it is from things they've seen before. And for a concept or an idea, there will be a relatively small number of overridingly good examples. And we call those exemplars. And then you can start talking about how different an instance is from a number of exemplars and try and work out which category it most, or which concept it most strongly belongs with. Maybe, if that's the way people naturally think about the world, maybe when we're trying to understand how our customers think about the part of the world where the problem is which they want us to solve, maybe we would do better if we got some examples. It turns out to be less useful than it might be to just ask people for examples of what they mean. It's useful to kind of walk them up to that. And in the Agile world, we tend to start with user stories, which I'm sure a lot of you are familiar with. Who here is using user stories to capture the existence of requirements? A few of you. Okay, so user stories look like this. This is one way of presenting them. It's not the only way. They talk about a role as a kind of person. And that's good, because if we want to get some examples, we know what kind of person to go and talk to. So as a hotel manager, in this case, I want to do something. I want to advertise my hotel. So the person playing that role has a goal that they want to achieve. And we can tell that they've achieved it if they get the value that's in that final statement. So as a hotel manager, I wish to advertise my hotel as prominently as possible so that I can maximize occupancy. And then we will know whether or not the system we have built has helped them achieve that, because we can go and find a hotel manager, we can get them to use the system, and then we can say to them sometime later, well, did you see your occupancy go up? Yes or no? That's not a perfect example. You can pick holes in it, but it's that kind of thing. There is a nice little checklist for a assessing the quality of stories developed by Bill Wake. He says that stories should be independent. They shouldn't refer to each other. They should be negotiable. User stories are very small. Traditionally, they are written on index cards, about that big. And that's deliberate. You can't put a long, rambling, complicated requirements statement into the story. There isn't enough space on the card. But what you can do is then have a conversation about more scope or less scope attached to the back of that story. Stories should be valuable. It's very easy when you're constructing those traditional requirements documents to put in lots of the system shall type of statements with no idea of why that's important. But if you can find out the value, maybe not literally the number of dollars or zlotys or whatever it may be attached to the story, but some idea of why it's important to somebody to have that story fulfilled, that can untangle some knots with requirements. Bill says that stories need to be estimable. I think he means estimatable. Estimable is a rather obscure English word which means of high regard. And yes, stories should be of high regard. But what he means is you can get enough information about them to estimate to an order of magnitude or so how much time or effort it's going to take to build the software to satisfy the story. They should also be small in the interests of controlling risk and measuring progress, and for a few other reasons. In an Agile project, we would want the development team to be able to complete many stories within a short time box, so stories need to be small. And the T on invest, they need to be testable. A good story has information attached to it, which means that a third party, not the customer, not the user, not the developer, but a third party could come along, look at the system as built, look at the story and say, yes, they join up, or no, they don't. And that's achieved through automated testing. Who does automated testing here, the systems they built? Maybe a third of you. Okay. And they should have a name so you can refer to them. So to achieve that testability, the approach that we take is to attach to a story acceptance criteria. And the acceptance criteria come in the form of examples. Exactly those examples that I was talking about before. The examples that the customer would use to show you what they mean by getting the thing they want in the story. And there will be several scenarios for each story, and we can give examples for each scenario. So for that not for the advertised motel, for the other one, for the other example story I had, the search for hotels, we might think of scenarios where there are no hotels found, or scenarios where there's one hotel, or scenarios where there's a few, or scenarios where there's a long list and we have to handle that in a different way. But we're still talking about requirements here. Finding the examples for the scenarios for the stories is still requirements work, but the people who are really good at this are testers. Testers are really good at thinking up cases. Well, what about this combination? What about that combination? Do we have enough of those? Do we covered these things? So in our practice, we have testers work with analysts, work with customers, or people like that, right up at the front of the process, because testers are good at thinking up examples for scenarios. They still do testing as well, and I'll talk a little bit more about the difference between those things shortly. And the way that we like to think about those acceptance criteria at Azulka in London is that they are checked examples. And this is an idea that was named by Brian Marek. And he says that a checked example is the use of tests and examples as tools for thinking about a piece of what the product owner wants with results that help the programmers. So it's a tool for thinking about the problem with results that help the people who are building the solution. which seems like a good thing. For the reasons I've already discussed, I believe, and a lot of other people have found, that thinking about the examples is much easier for customers than forcing them to think about rules and definitions. It comes much more naturally to them. And with the tools we have now, we can take those examples and we can turn them into automated acceptance tests directly. Who here is familiar with tools like Fit? Fitness, a handful of people. Selenium, quite a few more, okay. Cucumber, a few. Okay, so some of you have seen this kind of thing. For the benefit of those who have not, this is an example of a fit style of test. It's one of the examples that comes with Fit, which you can download for free. It really is a Word document. That's a screenshot of the test, the example inside Word. What the tool does is to take those tables and you write some plumbing, fixtures and adapters as they're called, so that the testing tool can run those examples against your system under test, and it will report back by coloring in the cells in the table whether it got the results that you said it should get. In this case, the first two rows, the first two examples, each row in that table is an example of a salary calculation. The first two examples check OK, but the third one does not. The calculation for holiday pay is wrong, so you see the expected result and the actual result are not the same, and it colors in the cell red, and it will generate reports that you can consume into your build server and fail the build, and so on and so on and so on. But the important thing is that writing those examples is something that you can teach your product owner, your customer, your user, however you think about them, to construct for themselves. Word is a very non-threatening thing. You can also, and I'll show you another example shortly, put these tables into Excel. Very non-threatening thing. Anybody who works in an office with a computer is fairly comfortable with Word and Excel. And they can happily sit and crank away more examples throughout the course of the project, drop them onto the test server, and see what happens. The job of the programmers then is to make all the pink boxes turn green. And you can track that, and that becomes a very valuable measure of progress. We can also construct scenarios in a more discursive form, where we literally tell a story. This is more the kind of BDD style of thing, with the given, when, then sort of construction. So given that some things are true, given some reference data for this scenario, when a certain event occurs, then certain behavior should be observed. And I'll show you again shortly, there are tools that can turn that into a test directly. Now, I said that testers are very good at coming up with these examples. It's the kind of thing that testers think about all the time. But constructing these examples is not testing. Testing is a thing which requires intelligence and creativity and imagination. And those are all things that people are good at. Taking those examples and checking to see if the system behaves that way is checking. And that requires repeated, fine-grained attention to detail. It requires a lack of imagination. It requires a lack of creativity. It requires the ability to do the same thing over and over and over again with great precision. And that's the sort of thing that machines are good at. So the process that we build with these kinds of tools, I think, leverages those two different things in the appropriate way. We say the people involved in the process can do the thing that people are good at, which is thinking up new stuff, creating new artifacts, challenging things. The machine can do the repetitive part, which is checking that all the details line up as you would expect. It makes me very sad to see people who are called testers, who sit all day chugging through scripts in Quality Center or something of that nature, typing in the input, pressing the button, looking at the output. Was it correct? Press the green button. Was it wrong? Press the red button, fill in the defect report. And doing that again and again and again, hour after hour, day after day, week after week. Who's seen that sort of thing? Yeah, about half of you. That's just a waste of human existence. It's a criminal thing. It shouldn't be permitted. It's literally inhuman. Machines should be doing that. If it can be, if the task is repetitive, then it can be automated. And if it can be automated, it should be automated. And people should do the imaginative part. So here's another example. This is from a real project. This is from an FX trading project. This is a real table, which I just copied out of the test suite. Some of the examples check, some of the examples do not. Fair enough. Job of the programmers is to make them all check. Examples in this form are mostly relational. So the tables for the examples, they don't all have this shape. There are other possibilities, but this is kind of the place you start. And this is very much to do with business rules. Each row in the table is an example of a calculation being done correctly. Inputs, outputs, expected values. So we have a tuple of that sort of shape given by the signature of the table. And then we have lots of examples that check OK or not. And I think of these examples as very much like gauges. So here's a picture of a gauge at the airport. You can dunk your hand baggage into it, and either it fits or it doesn't. And that's characteristic of gauges. They're kind of go, no-go kind of things. You could solve the same problem by having a person and a tape measure, and they get your bag and they go, well, yeah, that dimension's okay, and that dimension's okay. Oh, but that dimension's too big. Can't have this one. Get the next bag. Well, that dimension's okay, and that dimension's okay, but oh no, that dimension's too big. And that would be very slow and very labor-intensive and very expensive. And it would be an horrific job for somebody to have to do in the airport all day, right? Measuring luggage. But that's just like what the testers sitting in front of QC are doing. Instead, they have one of these, and people come along and they watch, somebody's kind of vaguely paying attention, but you dunk your bag in, and it either goes in or it doesn't. And that's kind of, you don't have to think about it, nobody else has to think about it, you get a yes or no answer, you can churn these things out very cheaply, and so on. So I think of these checked examples as being like gauges. The question that we do have to address is where those gauges are applied to the system under test. Many of you may be familiar with this idea that systems have layers, usually presented as a vertical stack with a user interface at the top and a database at the bottom. Who's seen that sort of thing? Yeah, most of you. Very familiar. Okay, dead wrong. This is a very, very misleading description of how systems work. And if you think your system is constructed this way, then it's hard to see, I think, where the examples plug on to the system. This sort of thing is a borrowing from electronic engineering, where they talk about communication stacks being built this way. But it's not the way applications are built. And we should put this idea behind us. Applications really are a lot, or systems I should say, are a lot more like living creatures. They have an inside and an outside and a boundary in between. And where the system boundary is a question that's open for discussion. So if we're building a web-based system of some sort, we might think that the system boundary is there and that the browser is outside the system boundary. And we might think that some domain logic, model, sort of thing is inside the system, and we might think that the database that provides maybe persistence services or data coherence services, consistency services to that model, we might think that that's inside the system as well. In which case, the examples must plug onto the web server. That's the only thing that's outside the system where we can observe its external behavior. But we might choose differently. We might choose to say that, well, actually, the web server is incidental, and the database is incidental. Our system is the domain logic, and so that's the thing we're going to write the examples for. That's the place where the tools will plug onto to decide whether or not the system is working correctly. Or we might decide that, in fact, the browser is inside the system. And then maybe we've got a problem, because talking to browsers is not the easiest thing in the world. But there are ways of doing it. So we could, my diagrams may have gone a bit mangled in translation from Keynote to PowerPoint. But imagine that the browser is at the system boundary rather than just inside. So the browser might be the thing where the examples plug on. So the place in the system that the examples live is at or just inside the system boundary. And the system boundary is a design artifact. We get to choose where it is. And we get to choose where it is in the way that is most advantageous to us. Now, when that database maybe is, or that data persistence and consistency service is perhaps outside the system, we would add in to our examples reference data, which is going to be poked into that database at the system boundary, or made available on a data service, perhaps, that the system talks to. So for that FX trading example, again, this is the real reference data for those tests. Talks about the number of days into the future that the trade is going to be hedged. Talks about exchange rates between the currencies. It talks about how many days into the future banking holidays come. The thing that was difficult about this project, or one of the things that's difficult about this project, is that with FX trading, obviously, you have two different currencies from two different countries, always. One of the rules of FX trading is that you can't set up a future trade with two legs and have one of those legs occur on a day which is a banking holiday in the home territory of one of the two currencies. So you can't, now that's sort of already, that's confusing, right? In fact, I can see some of you going, what? And the business analysts who are working on this were finding it very, very difficult to write down a comprehensive set of rules for that. It's actually a hard thing, and it's hard because it relates to calendars, and calendars are hard because they're arbitrary. And it gets really bad when you start looking at holidays, because they're very arbitrary. Different countries have different working weeks. You can't trade shekels on a Friday because that's not a working day in Israel. Easter moves around through the year, and Easter in Catholic countries is different from Easter in Orthodox countries. And so on and so on and so on. Eid is particularly tricky. Does anybody know why Eid is a problem? Any ideas? Eid is a problem because it relates to the real moon. So Easter moves because Passover moves, and Passover is based on a lunar calendar. But it's based on a sort of theoretical lunar calendar that's been tidied up. Eid is based on the real moon, and the real moon sort of wanders around in its orbit, and it's not perfectly predictable. So Eid can start on a different day in, say, Indonesia than in Morocco. So that can be a problem. And so on and so on and so on. It's all very tricky. And the BAs found it very hard to write rules about this, but the traders could very happily give large volumes of examples And they did, thousands of them, actually. And again, this is real. I copied this straight out of the test database. What you can't see is that out here there are about a dozen more columns, and in those columns are formulae that look into these blocks of test data and tell us whether or not these are correct. So it's kind of self-checking, and the colors relate to different equivalence classes of examples that the testers worked out. So we had a very good idea about how good the coverage was. And as I showed you before, those are the results that came out of it at a certain point in the project. Eventually, they did get the whole thing to go green. In doing that, they found defects with other systems that the FX trading component was going to talk to. Because the examples, when they plug on to the system under test, they simulate the systems on the outside of the system boundary. And in doing that, we found that actually some of those systems outside didn't work correctly. And they didn't work the way they were supposed to. And so we sort of pushed the correctness sort of radiates out from the tests. And we found design problems with the imagined solution that they thought they were going to apply, because if it's hard to implement the tests, if it's hard to take those examples of correct behavior described at the system boundary, if it's hard to wire those up to the proposed implementation is probably wrong. So these artifacts, which are like tests but not really, but are based on examples that we created to understand the requirement, will tell us whether or not we've got a good design. Well, they'll tell us if we've got a bad design, certainly, which is at least half the battle. And so they built the thing, and they got all the pink cells to turn green, and they put it live, and as best I know, no reported failures, no known defects, which was a new thing for that team. They'd never seen that before, and it was quite interesting to watch them sort of in the week after deployment to the traders. They were all sort of just sitting at their desks waiting for the phone to ring, with FX traders screaming at them because the system didn't work, and that didn't happen. And eventually they learned that, in fact, they could get on with their lives and do interesting new things. Thinking back on that experience, I think one of the things it teaches is that because the examples are written in the language of the problem, because they're outside the system boundary, they're written in the language of the problem domain, not in the language of the solution, they delay abstraction. They delay the process that programmers love to do of working out the very most general solution to the very most general description of a problem that's probably quite a lot like the problem you've actually asked them to solve, although perhaps not. It forces them to think in concrete operational terms, which again is contrary to the message that's come out of computer science education. Excuse me, that's come out of computer science education for the last 40 years, which is that you're supposed to be abstract. You're supposed to be general. And that concrete operational reasoning is a bad and dangerous thing. But no, concrete is better. Operational semantics win, I think. You could ask if the system as delivered was correct merely because it behaves as required in all known cases. That seemed like a strange statement. A lot of computer scientists would say, no, that's not enough to show that it's correct. And in a sense, they're probably right. But I would suggest that that's a sense that maybe doesn't matter terribly much to working software engineers in industry. It's something to be aware of in the back of your mind. And there are other techniques to use in parallel with this, with these checked examples to get towards that sense of correctness if you need to. So some of my colleagues work on medical devices, very strict regulatory compliance, and this is not enough. And we know it's not enough, and they do other things as well. But still, we like the model where, so I think is due to Bertrand Meyer, where systems exhibit failures because they have defects in them because somebody made an error. And you can't stop people making errors. You can do things to reduce the number of errors they make, but they're still going to. Which means the system may contain defects, and it will contain latent defects, defects that you've never seen. And the thought that the experience of doing this kind of work brings to mind is that, well, if those defects are always latent, if they never show up because there never was an example of required behavior that ever triggers the defect to become a failure, then is it a defect? No, it's like, if the defect never fails, is it truly a defect? Don't know. It can apply equally well to sort of big, hairy back-end systems as well. We applied the same sort of tooling to this big message routing doodad in the back office of a more or less a bank. So now the examples are examples of correct routing of messages. A message comes in, certain messages go out, the correct messages must go to the correct places, incorrect messages must not be emitted, correct messages must not go to the incorrect places, and so on and so on. And so the examples described that going on. You can't really read this, but you sort of don't need to. The thing that was troublesome about this is that these messages are very big. And this was a few years ago, and I wouldn't do it this way now. But those tables with the messages actually went out kind of into the car park out the back of the building, and they were huge. And I wouldn't do it that way now. That was sort of slightly naive. But the mechanics of it worked very well. And we had very high degree of confidence that all the message flows through the system were as they should be. I thought I had another slide, but I don't. Okay. Okay. I'm not as well rehearsed on this as I should be because somebody dropped out. I wasn't able to come to the conference, so Wikash asked me to fill in, so I actually haven't done this talk for a while, but there you go. Yeah, questions? The man with the microphone will come to you. Yes, sir.
You said you wouldn't do it like this right now, so how would you do it?
I would have much more of a template for the messages and only specify the parts that changed, rather than specifying the whole message every time.
Thanks.
And that's a little bit dangerous because you're then drifting towards doing programming in the tests, which is very dangerous. But in this sort of case, that's probably what I would do. I thought I had in the slide pack another example of a case where the testing was done by comparing generated PDF documents, and what's in the tables is just references to the PDF documents. So we had ones that had been built by hand that we knew were correct, and we would refer to those, and then we'd have a URL pointing to those, and we'd have a URL pointing to the ones that were generated by the system under test. And then we had some tooling that knew how to do diffs on PDFs, and that's a lot of fun, believe me. But when you looked at the tables, they were very small, because they just said, this document, that document. And I would do something like that with this. I'd say, this kind of message, but with these things changed. Yes, sir.
In your example, you have shown examples of that were connected to user stories. But what if the user story refers to a very complex business process? Do you then chop it into smaller stories and then add tests to them, or make a huge suite of tests that tries to cover up a whole complex process?
If you remember the invest checklist, one of the criteria for a good story is that it is small. So I would cut it up into smaller stories, and there are good techniques for doing that. If you Google for user story mapping, which is a technique developed by a guy called Jeff Patton, Patton. He gives a very, very good description of how to do that, and that's what we do on projects where we have those big stories. Any more?
In your example with calendars, you said that the main logic was in figuring out which day is a holiday in a given country, which is not. Why are you not just testing if the calendar says properly on a given date if it's a holiday or not? Because I suppose that deciding that whether you can trade or not is pretty straightforward. Yeah, if you have 2 working days, then you can trade. If not, you cannot. So why don't you just test the calendars that provide information? Is it a holiday in a given country or not?
Well, that just pushes the problem one step further back, because you have to show that they get it right, and you still have to explain what is supposed to happen on those cases. So it's not as simple as just saying the calendar for country A says it's a holiday, therefore you can't trade. The job of the system was to suggest trades to traders. So it wasn't good enough for it just to say it would be a really good idea for you to sell rubles, except you can't because it's Easter in Moscow. Oh, game over. It had to suggest something more intelligent than that. Any more?
If I understood correctly, you said that your set of tests discovered that the outside system was even badly designed and badly working. So did you feed this data to the real working system to know about this?
Yes.
So didn't you break anything, or? Because
Sometimes, yeah. But that's a good thing, right?
But it's like you feed Amazon and give some fake orders, yes, and it involves some waste of money. So. Production server.
Oh, sorry, right, okay, yes, I see what you mean. I once heard of a case where even the test environment sprang a leak and started really making trades, and that was exciting. No, so but what you can do is, and what we do is you move through a number of different environments. So the developers will check the examples against kind of head of trunk in their development stream, and every now and again they will check against some pre-production environment that they're deploying into periodically. If you were brave enough, you might check them against an instance of the live system, but with everything else stubbed out. But you'd have to be pretty brave, yeah. But you can, in a lot of environments where we do this, they do have pre-production systems which are as close to live as you could want, and we would exercise the examples against that, yes.
Can you repeat?
Oh no, they were just other parts of the same bank's trading platform that turned out on closer examination to not work properly. Imagine that, something in a bank that doesn't work properly. No, that's right, yeah. That's right, read the papers, yeah.
Can you repeat the name of mapping's complex stories?
Who said that? Hello, yes. Yeah, the technique is called story mapping, and the guy who devised it is called Jeff Patton, Patton. No. Any more questions? If there are no more questions, then I guess we're done. We can all go and get a coffee before we go to Kevlin's talk. Interesting? Potentially useful? Yeah? Good. Thank you.